Morning, ladies and gentlemen. One moment. I think I'm going to turn off the fan so you can hear me. Okay. Today is the day that I'm going to finally get around to pouring this thing. Okay, and I can send it up to Keith up in Georgia. It's a lifting sling. A million people have, a million lifting slings have been poured in the past, but they had, in the Navy, they had oxyacetylene tanks, they had oxyacetylene hoses, and everything you need for a heat source. I had to adapt to a different heat source. What I'm using is the Wagner heat gun, which, according to the label here, can go up to 1250 degrees. Now I'm just trying to heat this up to 400 degrees, and it works. I got it up to 400 degrees. It's only been on 3 or 5 minutes max right now, and it went from 80 to now 152 degrees. The reason why I didn't do this any sooner than I did do this is because I had to have this made on my 3D printer so that it would hold it, so I don't have to hold it. And I had this had to get this to act as an insulator for everywhere except where the heat is hitting the side of this. It's already up to 163, 165 degrees. It just turned 165. So I have every reason to believe that this is going to be able to bring this up to 400 degrees with no problems. Okay, then I'll dial it back and try to maintain it. I have over here, let's see if I can get you turned over there. It looked like dust. Watch my finger for a sec. Hold on a second. I see dust on this lens, and it isn't going to be very cool for you to try and watch things when I got dust on it. I'll be right back. Okay, well, I've taken it out of the holder just long enough to be able to show you. This will be kind of shaky, but you'll still get it to understand it. Now, I got this set up over here to get heated up by this hot gun. I don't know how long. I don't know if I would use this if I was doing this professionally, because who knows how long this would actually work. I got it at Harbor Freight, and it's doing a good job now. Matter of fact, it's up to 210 now. Starting to warm up the blanket here, the fiberglass blanket, insulating blanket. But it's already gotten to 217 degrees, so it's doing a dang good job. All right, that's how this is gonna do. All right, here's my little setup for the zinc. I got to bring that to 900 degrees. Okay, once I bring that to 900 degrees, I can take it over to here and pour it. I was going to use this infrared thermometer to keep an eye on that right there, but I wasn't getting a good surface because everything is all curved and is all angled, and so I wasn't able to get a flat surface. But I did find my nice little oven thermometer, and seeing as how this is only going to 400 degrees, and this could easily be put into an oven to be used at 400 degrees, I utilized it. I've got it stuck pushing against the surface of the inside of the socket, opposite of where it's being heated up. So you know it's being heated up here, and it's traveling around to the sides to heat up the rest of it. Once this detects this is at 400 degrees, it's already 248 degrees, I know that this will be 400 degrees. as per the instruction. Now I got to start heating this up, and got to get it to 900 degrees. Now I don't know how long it's going to take. This will be the first time I've used this setup to bring it to up to temp. The good news is, even if this infrared, the laser type of thermometer, if that don't work, doesn't appear to be working, I have my immersion pyrometer that I bought 3 or 4 months ago that I can have on standby. I'm hoping that this will work. It'll be a lot faster. Just got to make sure I don't go over 900 degrees. I don't know when that's going to flash off. We used to have a lot of manganese bronze. It's really a yellow brass, but they call it manganese bronze because of the amount of manganese in it. It's a nice strong, it's a really pretty brass that you want to use for high strength applications, and even if you wanted to use it for plaques. We used to use it for plaques all the time, so that we would be able to buff it up nice and golden looking. I'm hoping that this will watch that good enough where we can not miss the temperature. Well, as I was about to say, we used to use manganese bronze for all kinds of stuff, and we knew it was hot enough for even the thinnest of stuff. When we started to flash the zinc, we used to have a column of white smoke coming straight off of the metal going into the vent, and we knew that was as hot as we ever wanted to get it, if we ever had it for thin things. Okay, so I just wanted to, before I started all that up and making more noise, I wanted to show you my rig, and I'll bring you guys back when it comes time to pour this. Okay, I'm not gonna do it for both sides on this video, because it's the exact same thing on both sides, despite the difference in sockets. It's the same cable. It's the metal is the same. It's steel. It's even galvanized, it looks like, and it's everything else is the same. So once I get this going, this is at 400. It's at 302 right now. As soon as that's at 400, I dial it down some, keep it to 400, and then get that poured. I'll bring you back when I'm ready to pour. Okay, temperature's at least 400 degrees on this, maybe 415 now. The zinc is molten. I'm going to get this junk out of the way. And I'm going to have to turn on the vibrator now, so you won't be able to see, or rather hear, anything I do, but hopefully you'll be able to see. Well, the thing I was worried about didn't happen. I've never used this heat caulking before. And I was worried that it was going to, you know, generate a bunch of smoke and crap had come up in here and mess up this. Oh, that's right. It's got an automatic cooling shutdown stuff. I thought the breaker had tripped again. Anyway, that's solid right now. Yep, and it didn't pipe badly, so it'll be all right. That came right off. And apparently the zinc came all the way to the bottom because I've got what appears to be kind of a powder and burn look to the stuff. Oh yeah, came all the way to the bottom. Let's see if you can see it. See, I hope you can see this. See the silver all the way down to the bottom? Okay, that is the zinc. So, that turned out good. Oh, this didn't turn out good. That cockroach is not going to appreciate that. All right. So I'll let that one cool down. I need to get you up here a little more. Now if you can, you got to try and bend this, you know, to where it's almost in a straight line. So I'll go ahead and pour this one, and I'll clean it up and I'll send it up to Keith, and hopefully he'll have some use for it up there. I darn sure don't have any use for it here. Okay, I lift nothing except with my back, which is getting not too strong anymore, given that I'm over 64 now. So I will I'll heat this up, and maybe I'll turn you, I mean, it was a very short thing, so maybe I'll heat this up and turn it back on again and let you see if there's any difference between the first one and the second one. Okay, be back in a little bit. Okay, that's come up to 400 degrees. It's actually 401 right now. Time to take this out and let it cool. Time to turn this on. Not needed anymore. The vibration is really only needed as I'm pouring this. Okay, once it's poured, I know because of this vibration all the air has been knocked loose from the wire in there, and we don't have any air pockets in there to contribute to a failure when this is possibly weight tested. Okay, now we can turn this off. The one good thing about this is that Wagner's got a cool down circuit set up in it, so it doesn't immediately cool down, or rather it doesn't immediately turn off and allow the coils inside to just sit there and fester. That might contribute to their failure. But they let cool air, or at least ambient temperature air, go over it to try and cool down the coils in there, so that they don't stay super hot out in a oxygen rich atmosphere and burn up like the tungstens or the terminals in the old or the newest lamps, the bulbs, did in the beginning, before they realized that it was because of the hot filament inside the bulb coming in contact with the oxygen that made the filaments burn up so fast. Once they went ahead and put a vacuum or put a different atmosphere inside those lamps, that didn't happen anymore. Okay, now this is ready to go. You can use it, you can lift it, use it as a lifting sling immediately after you use it. Well, I'd let it cool down first. Now, if you're making it for yourself, you have the option to take your chances. Okay, if you're making it for somebody else, like I am, I'm in the strongest terms advising who's going to receive this to have it weight tested. Okay, now I know in my heart it's good. I followed all the instructions, and if you follow all the instructions in that that instruction, this combination is supposed to be as strong as the working strength of this cable by itself. Okay, so I'll get this down, put it in an area where it can cool without touching anything, and then I can get this ready to be boxed up and sent to Keith. Okay. Oh, by the way, the zinc did come all the way down to where the heat resistant caulking was touching, and so I know that all of the not filaments, but the wire strands in there have been encapsulated and bonded with the zinc. Okay, if nobody overweight tests that, and I don't see any reason why they might. I mean, I wouldn't put that in at a business where you're going to have bunches of people walking underneath it without any sense. But if it's going to be yours, if just for your own peace of mind, have it tested by somebody who weight tests cables and slings. Okay, it'll be then guaranteed for at least a certain amount of time that thing ain't going to fall apart when you're trying to lift something heavy. Okay, even if Keith doesn't send that off to get it weight tested, I have a very good feeling that that's going to lift whatever he needs to lift inside his shop. I mean, I think I read that size wire is supposed to be able to lift 45,000 pounds. Keith ain't gonna lift that much. I'd be surprised if he lifts a 10,000 pound item in his shop, which is what I'm sending that for him to use at. And even that, I don't know if I don't know what kind of gantry crane he might have. If he's got a real short one, that might be too long for him to use. Okay, but I know darn sure I can't use it here. The only one that can possibly use it is Keith up in Georgia. Him having a brand new shop, him needing to lift heavy things if he's going to machine it, and you know, this will do it for him. All right, but I strongly suggest, Keith, please test it. Have it tested, even if you only have it tested for 10,000 pounds, or the max temp, or rather the max weight that you're going to lift with it. That in your experience that you're going to lift with it. Okay, now this zinc over here, I got plenty left over. I could probably do another 2 or 3 cables worth. This zinc, may as well put my safety stuff back on, is not going to be used for anything more than perhaps some kind of a structural thing that I'll be making in the little foundry. Okay, I'll put you looking over there. And what I mean by structural things, this is a zinc alloy. Okay, now it actually is an actual zinc alloy rather than just a combination of crap that they threw in the pot. Okay, in the, I don't know what, from 1900 until about 1960, they used to have a pot where they put low melting temperature stuff in and make stuff like decorative stuff for their cars, and like handles for the windows inside the cars made out of what we called pot metal. I already explained why it's called pot metal, but for those of you who didn't see the other lecture or the other video, it was pot metal because that's the kind of metal they found in the pot that they melted the metal in. There was nobody knowing what was in there, not for sure. Okay, all they knew was that the vast majority of it was zinc. This came from a stand that holds up a big TV. I never used the stand because I put my TV up on the wall, but I saved this because I know that I'm going to be using it to, in the future, I'm going to be using it to make things. Like, for instance, I'm going to be making a wrapper for wrapping patterns inside molds, and it'll be this material will be plenty strong to take the abuse, and it'll last forever. So I'm going to melt this down. Now I don't see nothing in it, but you always assume that there's water in something that you're going to melt. So always wear your safety gear. Don't really have, there we go, that'll do that. Got these Hobart gloves. They're welding gloves over at one of the the local stores, and works real good. If you can't get your hands on a pair of inexpensive gloves used in the foundry, these are pretty good too. Although they get hot quick, not as quick as regular leather gloves, but they got hot quick. There's a layer of insulation inside here that it keeps them from getting as hot as plain leather gloves, the kind you would grind with. But what I'm going to do basically is just melt this down. If I had other pieces of zinc alloy in here, I'd melt it too, but That's the only one that I remember. And so, you know, it's one thing you got to realize, just like ice, everybody's familiar what ice is, frozen water. Just like ice, this stuff will not melt until that whole section is hot enough, as hot as its melting temperature. Okay? Ice will not melt and turn into water until the entire ice cube is above 32 degrees. But because heat from the outside touches the outside edge first and goes into the middle, the outside will flow away first. Okay? If you had the inside 75% of an ice cube would not go above 32 degrees, the rest of it ain't going to go either, because it's going to absorb all that heat and everything's going to stay frozen. Okay? So that is the last video for doing wire rope sockets. Okay, that was one of 3 different jobs that we had in the Navy. Okay, for those of you who I haven't bored to tears reciting what all 3 of them are, we did, you know, make castings with sand molds. We did wire rope sockets whenever that occasion came up, and we also repaired Babbitt bearings. Okay, now because I can't get my hands on a bearing, I don't have anything to be able to weld up a jig with to make a form for the Babbitt to, you know, solidify around. I don't have Babbitt. I don't have anything that is needed to physically demonstrate how do you do a Babbitt bearing. But in the near future, I will do the best I can on showing people and explaining how the proper way, the Navy way of repairing a Babbitt bearing, repouring a Babbitt bearing. Okay, I hated bearings because while we were using 1940s technology to pour the bearings, they were tested by 1990s sonic non-destructive testing using sound and all the stuff that the the calibration lab had. Okay, the names of the stuff is evading me right now. But you have, you know, if you're doing a bearing on the ships that I was on, the quality control people, when they made up a package, once the foundry poured the bearing, sent it down to the machine shop machined it, getting it totally ready to be put into the equipment, the non-destructive testing people had to test it to make sure that it was like 90% or better bond between the Babbitt and the steel shell or bronze shell, whatever you were trying to pour. We would get hot, as I was saying before the battery died and we were so rudely interrupted. We would get high scores on the percentage of bond between the Babbitt shell and the iron shell, or the Babbitt bearing, the Babbitt material and the iron shell. We would get at least in the upper 80s, if not the middle 90s. But their requirements were supposed to be past 95. You know, about when it came to that requirement, I think we had very few bearings that didn't finally make it. But after several times of us having to pour the same thing, it was rough. So I didn't like bearings all that much. Some people liked them. Maybe they had a better technique than we did in the foundries I was in. Anyway, so back to what I'm saying is I won't be able to actually pour a bearing to show you how to do it, but I'll be able to show you pictures and I'll be able to explain things verbally, like I did on, on the sands and all that stuff. Okay, so until next time, while this is slowly coming up to temperature, we will see you at the next video and Liberty Call. As I was saying before the battery died and we were so rudely interrupted, we would get high scores on the percentage of bond between the Babbitt shell and the iron shell, or the Babbitt bearing, the Babbitt material and the iron shell. We would get in the, at least in the upper 80s, if not the middle 90s, but their requirements were supposed to be past 95. About when it came to that requirement, I think we had very few bearings that didn't finally make it, but after several times of us having to pour the same thing, it was rough. So I didn't like bearings all that much. Some people liked them. Maybe they had a better technique than we did in the foundries I was in. Anyway, so back to what I'm saying is I won't be able to actually pour a bearing to show you how to do it, but I'll be able to show you pictures and I'll be able to explain things verbally, like I did on, on the sands and all that stuff. Okay, so until next time, while this is slowly coming up to temperature, we will see you at the next video and Liberty Call.